So today's lecture is on an introduction to torque and angular acceleration. So what we're going to cover today would be a recap of rotational kinematics and energy. You've probably seen this quite a few times already, but it's very important to know how the linear world relates to the rotational world. So we're going to do a quick recap of all the main equations. Go through a quick worksheet, number 19, for the moment of inertia. And then we're going to go into an introduction to torque. So we'll first present torque, how to calculate torque, explain what it is, and how it's related to angular acceleration. After that, I'll go through a practice problem and then end off with the back side of the 19th worksheet, which is an introduction to torque. So let's start off with the recap first. In the past few lectures, we've talked about rotational kinematics. So we have linear kinematics with these equations. So just remember, we use x for displacement, and in the rotational world, x now becomes theta for the angular displacement. Velocity v now becomes omega for angular velocity, and acceleration a becomes alpha for angular acceleration. So this angular acceleration from rotational kinematics can also be related to Newton's second law for rotational motion. So we're going to be talking about that today as well. So in terms of the kinematics equations between linear and rotational worlds, the format is the same for both, it's just the letters that have changed. The next thing that was important was the connection between linear and rotational quantities. So we had three different equations. We had velocity being equal to r times omega, centripetal acceleration being equal to r omega squared, and tangential acceleration being equal to r times alpha. So as recommended, these would all be good equations to put on your formula sheet. Next, we talked about rotational kinetic energy. We have the moment of inertia being the sum of all the individual moments of inertia in a particular object. So if you have 5 areas within your object at different distances from the center, then you would have to add each of these separately. So I total would be equal to, let's say there are 2 objects. So example, 2 objects, you would have m1 r1 squared plus m2 r2 squared to get the total moment of inertia of the object. Apart from that, you also have kinetic energy in the rotational world. So instead of Ke is equal to 1/2 mv squared, we have Ke being equal to 1/2 I omega squared. And the important thing to remember here is that once we move on to rolling motion in the next few lectures, the total kinetic energy is going to be the translational kinetic energy. So this would be translational plus the rotational kinetic energy, because an object that's rolling down and is in motion is both going to rotate and have rotational kinetic energy and also be moving, which means it has translational kinetic energy. So just as a quick recap, we should probably do an example about the moment of inertia. Last class, we mentioned that there are different values of k that are in front of that mr squared for the equation for moment of inertia. So instead of I being equal to mr squared, you might have I is equal to 1/2 mr squared for different types of objects. If you're looking at a rod, you don't have mr squared because it's not spherical, you have ml squared because you have the length of a rod. So this worksheet basically takes us through how we would even go about calculating the moment of inertia for different shapes of objects. So the main focus of this worksheet is a stick of length L that has mass m. It's rotating about its center. So keep in mind you have a stick that's a length of L. So stick that's length of L, and the center of mass of that entire object is probably right smack in the center of it. It's also saying that this stick is rotating about its center, so we can assume that it's rotating around this center. So next it states the correct value for the k factor, which multiplies ml squared, is 1/2. So the real value of the total moment of inertia is 1/12 ml squared. And just as many of you had asked in the previous class, where did this 1/12 come from? So that's what we're going to do today. We're going to derive this, and we'll try not to use calculus because this course doesn't involve calculus. So long story short, with calculus, we divide the stick into an infinite number of small segments of the same mass m, and use the formula mr squared for each one. But dividing the stick up into an infinite number of segments would really take forever, so we're going to try dividing it by half, and then dividing it into quarters, and then dividing it into eighths to see if we can get a better and better approximation of the true value of I. So the first question asks us to draw a stick of length L and mass m and split it in half. So why don't we go and do that? We have a stick. It's got a total length of L, and it has a mass of m. So that's the total mass. And we're splitting it in half, so that's the halfway point. Just remember, we can't forget about the axis of rotation, so let's draw this in red, and we can assume that it's rotating around that center axis. Afterwards, we have to take a look at each segment individually, and we also have to put a dot at the center of mass of each half. So when we're just looking at this segment and this segment, there is a center of mass for each of these segments right here, and they are going to be a certain distance away from the axis of rotation. So we'll call this R1, and we'll call this, R2. So now we have to try and figure out what these values are going to be, and of course what the mass is for each of these halves. So this would be the first half, and this would be the second half. Let's do an analysis on segment 1. We know that R1 is probably, let's see, 1, 2, 3, 4, 5 tick marks. That means from the axis of rotation here to this center of mass, it's L/4. So it's L/4 distance away from the axis of rotation. This also means that segment 2 R2 is also equal to L/4 away from the axis of rotation. Now we take a look at the masses. Each segment should have the same mass, but we've split the entire stick into 2 pieces. So that means the total mass, capital M, is just divided by 2. So this is m/2 and m/2. So now we have the masses of each segment as well as the distance that the center of mass of each segment is away from the axis of rotation. So if I want to figure out the total inertia or total moment of inertia, it's going to be I total is equal to I1 plus I2, which is equal to M1 R1 squared plus M2 R2 squared. It's equal to M over 2 L over 4 squared plus M over 2 L over 4 squared. So then I would have ML squared over 2 times 4 times 4. And that gives us 2 times 16, which is 32. Then we have the exact same over here, ML squared over 32. And in total, you're going to get 2 over 32, or 1 over 16, ML squared. And this is what we call the K factor, but we only split the stick in half, so it's not extremely accurate. The real answer, so this is the K factor, but the real K factor is 1 over 12. So if I divide 1 over 16 by 1 over 12, then this is only 75% accurate. Okay, so on to the next slide. We divided this into 2 pieces. We now want to divide it into 4 pieces to see if we can get a better answer. So we're going to repeat number 1, but now with the stick split into 4 pieces, or n equals 4. So if I split it up into 4 pieces, cut it in half, cut each one in half, but the axis of rotation is always here. So we draw this. And we're going to name this 1, 2, 3, and 4 for the 4 segments. Each segment has its center of mass in the center of each segment. And so I'm just going to put this in blue. We have R2, we have R1 for the distance that each center of mass is away from the axis of rotation. So then we have R3, and we have R4, like that. So looking into each segment, I have segment 1, R1 is going to be equal to, we know the total length is L, so this is in quarters, which means we have L over 4 going into each end of the segment, but we want halfway points between the segments, so that means it's L over 4 divided by 2 to get to the center point. So that means R2 from here to here is L over 8. Oops. So R2 for segment 2. You should probably keep track of these. R2 is L over 8, which means here's another L over 8 to make L over 4, and then I have 3L over 8 for R1. Segment 3, R3 is equal to L over 8, and segment 4 is equal to 1, 2, oops. So 1, 2, 3, L over 8. Okay, hopefully that makes sense. Now we want to figure out our mass for each segment. Luckily, this is a stick with uniform density across the entire stick. So if the total mass is capital M and it's broken up into 4 pieces, we know that the individual masses are M over 4. Okay, so now we calculate the total moment of inertia. And that is going to be I total is equal to I1 plus I2 plus I3 plus I4. So that's M1 R1 squared plus M2 R2 squared plus M3 R3 squared plus M4 R4 squared. That's going to be capital M over 4. R1 is 3L over 8 squared plus M2, which is M over 4, L over 8 squared. And this one for the third segment is the same as the second segment, so we can just say this is 2M over 4. The fourth segment is pretty much the same as the first segment, so we can say this is 2M over 4, just so we have 2 of each. And because I'm running out of space. So now I have these, just going to add up the fractions. Should probably simplify first, so this would be M over 2. I have 3 times 3 times L squared, so that's going to be N L squared. 8 times 8 gives me 64. This is going to be M over 2, and this is L squared over 64. And that gives me, so this gives me 9 ml squared over 128 plus 1 ml squared over 128, which is 10 over 128 ml squared, which is 5 over 64 ml squared. Okay, so now we have this new K factor, and we now compare it to 1 over 12. So percentage-wise, we have 5 over 64 divided by the true value of K, which is 1 over 12, and we get 0.9375, which is equal to a 93.75% accuracy for a 4-segment stick. So it seems like we're getting closer and closer to the true value of K. So we can make the assumption that the more pieces we chop up the stick into, the more accurate our answer will be. So as one last exercise, we're going to split it up into 8 pieces. So we have a stick of length L and mass M. We've cut it in half. We do have the axis of rotation being this way, so that's something we can't change. We cut it in half from before, and now we're cutting it in half again. So now we have 8 pieces to this stick, and each piece has its own center of mass. And each center of mass is going to be a certain distance away from the axis of rotation. So if I were to split the scale up from here to here, say this is like this, the center of mass is at the center point of each of these 1/8 segments, which means that the scale is going to be in 1/16. So this is 1/16 So starting from here, we can label each of these as 1, 2, 3, 4, 5, 6, 7, 8. So we're going to have two segments, 4 and 5, who are at 1/16th distance away from the axis of rotation. We then have 3 and 6. They're both going to be 1, 2, 3 over 16 units away from the axis of rotation. So why don't we write that down? We have segment 1. Actually, let's just make this easier. We have our segments, and we have our R values for each segment, and we have our mass for each segment. So we have 1, 2, 3, 4, 5, 6, 7, and 8. So the easiest thing is the mass. It's broken up into 8 pieces, so each of these is just going to be m over 8. The only thing that's going to be different is the distance away from the axis of rotation. So as we've said, segments 4 and 5 are 1/16th units away from the center of axis. 3 and 6 are going to be 3/16ths away from the center of axis. We have 2 and 7 being 1, 2, 3, 4, 5/16ths. Oops, not 5, 6. 5/16ths away from the center of axis. And 1 and 8 are going to be 1, 2, 3, 4, 5, 6, 7/16ths away from the center of axis. So the next step is just to calculate the total moment of inertia. So I total is equal to the sum, where you start at 1 and go up to n equals 8. And you have mi ri squared. So as we've noticed, there's going to be two values that are going to be the same. There are these ones, and these pairs. So that means there's 2 times m over 8 of 1 over 16 squared plus 3 over 16ths squared plus 5 over 16ths squared plus 7 over 16ths squared times L squared. When you punch all of these into the calculator and get a giant fraction out of it, you're going to get 2m over 8 times 84 over 256 L squared. (21 over 256 ml squared). So this is now your new K factor, and when we're comparing it to 1 over 12, now we're going to figure out the percent difference for both of them. We have 21 over 256 divided by 1 over 12, and we get 0.9844, which is equal to a 98.44% accuracy to the true value of K equals 1 over 12. Okay, so that basically goes through the entire first page of the 19th worksheet. Oops, I forgot a question. Number 4 says, what generalization can you make as n approaches infinity? So basically, if we continue chopping up the length into an infinite number of pieces, we can assume that as n approaches infinity, k is going to approach 1 over 12. In other words, as n approaches infinity, we get a more accurate representation of the k factor. So hopefully that explains how different shapes can lead to different calculations for the moment of inertia. Now that we've finished this part of the worksheet, we want to move on to an introduction to torque. So torque is probably something that most of you haven't learned yet, but if we're trying to relate the linear world to the rotational world, so far we've done linear kinematics. So there's acceleration, there's velocity, and there's displacement. But the one thing we haven't really touched on is force. So because we do have acceleration in the linear and the angular rotational world, it means that there should probably be some sort of F equals ma in the rotational world as well. And when we look into the rotational world, torque is the equivalent of force from the linear world. So what is torque? Torque is the rotational equivalent to force, and it is in units of newtons. So, units of newtons for linear force. So we're going to take a look at torque, which doesn't have units of newtons. It's going to be a little bit different after we define it. So think of loosening a nut with a wrench. So in the picture to the right, you can see this nut, and we're trying to loosen it with a wrench. And if you've ever used a wrench before, you'll probably notice that it's easier to apply a force down the arm of the wrench than it is to apply a force closer to the axis of rotation. So that is torque at play. You have to apply a force a certain distance away from the axis of rotation. The farther you get from the axis of rotation, the larger this distance vector is, which means the less force you have to apply in order to equate to the same amount of total torque. So why don't we present the equation for torque? Keep in mind the distance away from the axis of rotation is a vector, and so is the force that you apply. So back then when we looked at work, it was the dot product between two vectors. Torque is going to be the cross product between two vectors. So this is the cross product. So I won't get into too many details about this, but a dot product is going to be a vector A dotted with B, and it's going to be equal to AB cos theta for the angle between the two vectors. A cross product is represented by A crossed with B, and it's equal to AB sine theta, where theta is the angle between the two vectors. So it's really important to remember that torque is the cross product between the distance vector as well as the force vector. So as I've explained, that is how you would represent the cross product in a mathematical formula of just magnitudes. So you have torque being equal to the magnitude of the radius of the distance of the force acting on the system times the magnitude of the force times sine of theta. So if we look to the image on the right, we now have a certain force vector being applied at this point, and that point is a certain distance away from the axis of rotation. And the angle between the two vectors is theta. So just like with work, how we wanted to find the amount of force acting along a certain distance, we also want to find out the amount of force acting along the radius, or this portion. But that means when we do this calculation, even though torque is the rotational equivalent to linear force, the units are not newtons. We have some sort of distance r multiplied by some force in units of n. So your units are in Newton meters. So from before, I mentioned that because we have linear and rotational kinematics, we should probably introduce a rotational version of Newton's second law. So from before, we know that F is equal to ma. We also know that acceleration, so linear acceleration, is equal to r times alpha. So if we were to just solve for alpha, to switch everything to the rotational world, we can put a into this equation and solve for alpha. So you end up getting to here. And in order to make things a little bit easier, we can kind of think about how we know that tau, or torque, is already equal to Rf, and that moment of inertia is equal to mr squared. If we wanted to, we could just multiply the top and bottom by r over r, and we can get Rf over mr squared. And then we can convert this to tau for torque, and we can convert this to I for moment of inertia. So then we can rewrite angular acceleration as torque over the moment of inertia, or we have torque being equal to the moment of inertia times alpha. So instead of F equals ma, we've kind of rewritten it in terms of our rotational equivalence. The rotational equivalent of force is torque, so we have T, or tau. The rotational equivalent of mass is the moment of inertia, I, so we have I over here. And the rotational equivalent of acceleration is angular acceleration, or alpha. So it's just F equals ma, same equation, but in rotational terms. If we wanted to figure out the net force, or the net torque, acting on a system, then you need to sum up all of the individual torques to get the total, just like with Newton's second law questions from before. So another way of writing this would be, the whole slide is just the same, the only difference is just this. If we want to find the net torque acting on a system, just keep in mind you will have to add up several torques to get the net torque. So now let's go through a practice problem. Here we have a fisherman who's dozing when a fish takes the line and pulls it with a tension T. So the spool of the fishing reel is at rest initially and rotates without friction as the fish pulls for a time T. If the radius of the spool is r and its moment of inertia is I, we want to find three different things. We want to find the angular displacement of the spool, which we know is delta theta. We want to find the length of the line pulled from the spool, which is probably a linear quantity, so delta x. which we already know delta x is equal to r delta theta. And we want to find the final angular speed of the spool, which would be omega f. So why don't we start off by drawing a diagram and then trying to figure out these three values. So okay, so let's first draw some sort of the spool of a fishing rod. So we have this. Here is the axis of rotation. We know that this is the radius, and we also know that there's going to be some sort of spin that's going to cause a change in the angle. So it's going to be delta theta for the angular displacement. We also know that there's going to be some sort of handle, and this part isn't really important, but there's usually a handle that you crank so that you can reel in the line. So this is the fishing line that's attached to the spool. There's going to be a tension force, T, pulling away from what we're looking at. We also know that the wheel is spinning this way with some sort of angular speed. We're told that it starts from rest, so omega 0 or omega I for initial is 0, and we want to find omega f at some point. The other important thing to remember is the tension coming from the fishing line is probably going to be at a right angle to the spool itself. And we also know that if the spool is turning, it's going to release more of the fishing line, and that means that the fishing line has traveled a distance of delta x, which is equal to r delta theta. So number A, we want to find delta theta. So before we can even approach this question, if you have your formula sheet handy, you know that torque is equal to Rf sine theta, where theta is the angle between the two vectors. We also know that alpha is equal to torque over the moment of inertia, so that's the new angular acceleration equation that we have. So why don't we start with those two? We have tau equals to Rf sine theta. We already said that the angle between tension and R, so we have capital R being the magnitude of the displacement vector times F, and the force is tension, so we have T, and we know that the angle between these two is 90 degrees. Sine of 90 is equal to 1, so that means this is just equal to R times T. After, we have angular acceleration, it's equal to torque over I, and that's equal to RT over I. And our goal is to try and find delta theta. And if we already know angular acceleration is RT over I, we know that omega I is equal to 0. We don't know what omega f is, but we do know that a certain amount of time has passed, and it just gives us t, so we'll use t. So we have 1, 2, 3 values, which means that we can use a kinematics equation to solve for this. Delta theta is going to be equal to omega it plus 1/2 alpha t squared. The first term goes to 0 because it starts at 0. Then you have 1/2 RT over I t squared, which is equal to RT little t squared divided by 2I. So that answers the first question for part A, find delta theta. The next question asks you to find delta x. So we're going to move on to the next slide and go to part B, which is find delta x. We already know the equation for delta x is r delta theta. That's equal to capital R delta theta was RT little t squared times divided by 2I. So delta x is equal to R squared capital T little t squared divided by 2I. And last but not least, we have part C, which is asking us to find the final angular velocity. So we have find omega f. That's equal to, so let's first write out what we know. Omega I is 0. Alpha is equal to RT over I. We know that the time that has passed is t, so we can easily solve for omega f by using a kinematics equation, this one. So omega f is equal to, this one's just 0, alpha t, omega f is equal to RT little t divided by I. And that answers all three questions. Next, there is a group worksheet. This is the second part of the, or the second page of the 19th worksheet that was posted. And it goes through an introduction to torque so that you get used to using the different equations that we've just presented. And so the question here is saying an electric motor drives a grinding wheel, or basically a solid disc, of mass 3.0 kilograms and radius 8.0 centimeters. There is a frictional torque, and both the torque due to the motor and the friction are constant. So the key thing here is that we have two torques to look at. So we have a frictional torque similar to a frictional force, and we also have a motor torque similar to the motor force. So when we're trying to find the total amount of torque acting on a system, we have to consider both types of torque. So when the motor is switched on, it takes 4 seconds for the wheel to speed up from rest to 600 RPM and 42 seconds for the wheel to stop when the motor is switched off. We're trying to find the individual values for motor torque and the frictional torque. So just a quick recap from before, the rotational equivalent to Newton's second law for linear motion is this. So it's like F net equals to ma, but we now have torque net is equal to moment of inertia times alpha. Torque is the rotational equivalent to force, which results when the force doesn't act through the center of mass of the object. So the following exercise or worksheet is just going to step you through the solution to the problem above. So first, we're going to have to draw two diagrams for the rotating disc. One for a positive spin and one for a negative spin. So we'll just call it spin up and spin down. So we have spin up and we have spin down. And so we're going to draw the two discs. And the axis of rotation is right in the center. So this is the rotation. Just draw this a little better. So what this essentially means from spin up to spin down means two different scenarios. The first scenario is when you've switched on the motor and it's taking 4 seconds for the wheel to speed up from rest to 600 RPM. So this is spin up or speeding up. This also means that your acceleration is probably increasing in the positive direction, so you have alpha 1. It means that you have a frictional torque slowing it down, so we call this tau F, and you probably have a motor force or motor torque going in this direction. Well, hopefully this makes sense. This is in the positive direction, this is in the negative direction. Now, when you're spinning down, or essentially slowing down, so let's call this, you've essentially turned off the motor, and your acceleration is probably going to decrease, so that means your acceleration is going in the opposite direction now, and because there is no more motor torque, it means that the only thing that's here that's acting on the system is your frictional torque in this direction. Then, for both of these scenarios, you have R being the radius. The value of radius is 0.08 meters. And you have the mass being a total of 3 kilograms. Okay, so we have these two different cases, and we're now going to look at each case individually because one is spin up, the other is spin down, and we're going to come up with two separate equations for the net torque. So in the spin down case, so the second case where it's slowing down, we want to calculate the frictional torque. So the question is, why did I start here with the second case? So this is case 2. It's because there's only one torque acting on the system. So that's the easiest one to analyze. So that means we have the net torque being equal to the sum total of all the different torques. We have TF, and it's equal to the moment of inertia times the acceleration experienced in the second case. Now we also know that omega F is equal to omega naught or omega I plus alpha T. So if we're able to figure out alpha, we have alpha is equal to omega F minus omega I over T. So the values that were given from the question, because it's on a previous page, I should probably rewrite this. Because this is spin down, it means that it's going to slow down to a speed of 0. That means it's going to start from the maximum speed of 600 RPM. So omega I is equal to 600 revolutions per minute, which is equal to, anyway, might as well convert this. We have multiplied by 2 pi r over 60 seconds per minute which is equal to 20 pi radian per second. And it also says that it takes 42 seconds for the wheel to stop, so we have t equals to 42 seconds. So we have initial speed, final speed, and also time, which means we can calculate for alpha. And specifically, this is alpha in the second case, so we have alpha 2. Alpha 2 is equal to 0 minus 20 pi divided by 42, which is equal to negative 1.496 radians per second squared. So this makes sense. The acceleration is negative because it's slowing down in the second case. So we're also given the equation for net torque. We're not given, we were able to solve for it up here. So now that we have the angular acceleration for the second case, we can plug that in to tau f is equal to I alpha 2. And it seems like we're still missing something. Seems like we're missing I. So remember from our previous exercise, I was equal to 1/2 mr squared for a solid wheel, which is 1/2 3 times 0.08 squared, which is equal to 9.6 times 10 to the negative 3 kilogram meter squared. So now I'm free to calculate my frictional torque. So 9.6 times 10 to the negative 3 times negative 1.496, and that means my frictional torque is equal to 0.0144 Newton meters. Okay, so one down, one more to go. We're going to move on to the spin up case. So in the spin up or the speeding up case, we now have both a motor torque acting on the system as well as a frictional torque. So you have your net torque acting in the first system being a sum total of all the torques. The motor torque is acting in the positive direction, whereas the frictional torque is acting in the opposite direction, and it's equal to the moment of inertia times the initial or the acceleration in the first case. So we're going to use the exact same method as before. We can get the angular acceleration by using this equation. So it was omega f minus omega naught, or I, divided by t. The only difference now is that omega I is 0 and omega f is 600 RPM, which is 20 pi radians per second. So alpha 1 is equal to 20 pi minus 0 divided by the time it takes isn't 42 seconds, but rather 4 seconds to speed up. So divide by 4, and that gives us 5 pi radians per second squared. Okay, so now that I have alpha 1, I want to be able to solve for tau m. So tau m minus tau f is equal to I alpha 1. Tau m is equal to I alpha 1 plus tau f. Tau m is equal to, we already know the moment of inertia, 9.6 times 10 to the negative 3. Alpha is 5 pi, and we want to add the frictional force or torque that we found before, 0.0144, and we have the motor torque being equal to 0.165 Newton meters. And that covers both of the torques that are present in the entire system.